I research how a crop disease is spread by insects. Let me introduce you to the blue-green sharpshooter. It's one of the major insects that spreads Pierce's disease of grapevines, which costs California over $100 million per year. The disease is caused by bacteria that survive in the foreguts of the insects, and as the sharpshooters feed on plants, they spread the disease. Blue-green sharpshooters feed on grapevines by piercing plant tissue with their proboscis, which is indicated by the arrow, and it's also shown on the next slide. This diagram illustrates the proboscis piercing plant tissue during insect feeding. The insect sucks plant juices into its foregut and then spits them back out. It's during this process of repeatedly sucking in and spitting out that the disease is thought to be transmitted. I predict that fluid drag forces during the spitting out process play a major role in disease transmission. I created a 3D model of the foregut and simulated the fluid dynamics of spitting. My results predict that there are fluid drag forces in some regions of the foregut that are high enough to detach bacteria. Once the bacteria are detached, they can be spit into the plant and cause disease. And high fluid drag forces are not the only reason I have for my flow-driven transmission hypothesis. There's also the bacteria colonization patterns in the foregut, which mirror fluid dynamic predictions. But that's not easy to show at the current magnification of the model. There is a region of the foregut that has been specifically linked with bacteria transmission. It's composed of the magenta and teal portions of the model. Now, the bacteria attach to the inner walls of the foregut, which are hidden in this view, but they can be visualized by taking 3D molds of the magenta and teal portions of the model. These molds represent the segment of the foregut that's of interest. It's been researched more closely in previous studies of bacteria transmission. I plotted my fluid dynamic simulation results within the 3D molds to obtain the rainbow-colored heat maps of fluid drag forces shown here. Now, in these heat maps, the dark blue regions indicate locations where there are low predicted drag forces, yellow indicates high predicted drag forces, and dark red indicates very high predicted drag forces. Now, let's compare these results with locations where the bacteria have been observed soon after they attach in the foregut. And that's what these rectangles represent. And I obtained these rectangles, I derived them based on a previous publication, but here's what you need to know about these rectangles. The rectangle on the left corresponds with the fluid dynamic simulation on the left, and the rectangle on the right corresponds with the simulation on the right. Blue circles indicate locations where bacteria were often observed. Yellow circles indicate locations where bacteria were seldom observed. And the blank regions indicate locations where the bacteria were never observed. So what I want you to notice is that bacteria colonization patterns mirror fluid dynamic predictions. For example, in this rectangle on the left, down at the bottom, there's this cluster of blue circles that corresponds with the region in the simulation on the left that has lots of blue. Likewise, down at the bottom of the rectangle on the left, there's this cluster of the darker blue circles that correspond with a region in the simulation on the right with the lowest predicted drag forces for that simulation. Now, just above that is a region that I'm calling a saddle-like region. It has a high point in the middle and low points above and below that. So the predicted drag forces are higher in the middle and they are lower above and below the saddle point. So this can be compared with the rectangle on the right, where we have saddle-like colonization patterns. In the middle, it's less likely to observe bacteria, but then above and below that, it is more likely to observe bacteria. And that mirrors what we see with the fluid dynamic simulation. So one last example here, up at the top of these rectangles, we can see that there's generally a low likelihood of observing bacteria in these segments of the foregut, and these corresponds with the top of the fluid dynamic simulations with lots of the yellow and red predicted drag forces. So those are high drag forces. And to summarize what I'm saying on this slide is that bacteria colonization patterns mirror fluid dynamic predictions in the foregut, and that there are these regions with yellow and red predicted drag forces that are much higher than those required to detach bacteria. Therefore, Fluid dynamics likely play a major role in detaching bacteria from the foregut, and I want to contextualize that conclusion within a slide that we saw before. What I'm saying is that fluid dynamics in this region of the foregut likely play a major role in detaching bacteria. Once the bacteria can be are detached, they can be spit into the plant and cause disease. So this conclusion of flow-driven transmission is the main point of my talk so far. And it would have been difficult to communicate that point if I hadn't made heavy use of graphic design. My conclusion is based on an analysis that the audience isn't familiar about. It's based on a small section of insect anatomy during a specific insect feeding behavior. If my communication was not effective, then audience members could have been lost easily. And this is part of why my research has driven me into a journey of improving the effectiveness of my science communication, because even entomologists can sometimes be thrown off by the complexity of my work. Now, this is how I think about my 3D model. It's a curved structure that kind of resembles a spaceship, and it represents the real foregut that is inside the insect head at the location indicated on the slide. So that's how I think about the 3D model, but that's not really how an entomologist would likely think about the foregut. Entomologists are more used to seeing microscope images like these. These are obtained from dissected insect heads where these two parts of the foregut are obtained in these, are shown in these microscope images. So before those insect heads were dissected, the two halves of the foregut were pressed together inside the insect head, and they form a shape like the one represented in my 3D model. But that's often hard for people to make a connection between these images and that 3D model. So I've had to rely on graphic design to make that connection for people. And here's what that looks like. I cut my 3D model in half. I split it in two along the dashed line shown here. And then I hinged the two halves of the model outward as indicated by these arrows. And what I obtained looks like this. I've got two halves of the 3D model that were split along this dashed line. You'll notice that I also have these gray sections added in with the 3D model, and those aid for comparison with the corresponding microscope images. So one more thing that helps with that comparison is these false colors that I've added to the image simply for the side-by-side comparison. And what this comparison can do is it can help an entomologist gain a more intuitive understanding of my 3D model based on what they're familiar with. So I wouldn't start off a presentation to non-entomologists with this, but it is helpful for entomologists that have that type of background. Instead, in this presentation, though, I'm speaking mostly to non-entomologists, and I took a different approach, right? On the first slide, I had two images of an insect, and I showed where the proboscis is located on the insect. On the second slide, I showed how the proboscis is connected to the foregut, how the proboscis connects with the foregut and how those two things are related with the insect feeding behavior. And then on the third slide, I showed how I made a 3D model of the foregut and how I could make these 3D molds from my 3D model. So it's a completely different approach. What I did was I catered my presentation to my audience. And this type of presentation requires a lot of extra work, and I had to learn new things, but it made my research accessible to a wider audience. And so I think it's worth it. And I'm looking forward to seeing how my more effective science communication can contribute to the impact of my research. Thank you.